Today, we are here to also honor the 2020 IEEE Computer Society Sidney Fernbach Award recipient, Dr. Salman Habib.
The IEEE Computer Society Sidney Fernbach Award honors the memory of one of the pioneers in high-performance computers. Established in 1992, the award is given to an individual in recognition of outstanding contributions in the application of high-performance computers using innovative approaches. The 2020 IEEE Computer Society Sidney Fernbach Award is presented to Dr. Salman Habib of Argonne National Laboratory. Dr. Habib is recognized for pioneering fundamental physics applications from the smallest to largest scales on 3 decades of emerging forefront computing platforms. Dr. Habib is the director of Argonne's Computational Science Division and an Argonne Distinguished Fellow. He is a Fellow of the American Physical Society. Dr. Habib moved to Argonne after 20 years at Los Alamos National Laboratory. At Los Alamos, he first encountered parallel supercomputers, the thinking machine's CM200 and later the CM5, which was then the world's fastest system. Those early days have led him to supercomputing-driven forays in diverse areas such as dynamics of coherent nonlinear structures, beam dynamics and accelerators, non-equilibrium quantum field theory, and the formation of structure in the universe. He regards the role of supercomputers as engines of scientific exploration and discovery to be one of key prominence, then as now. Dr. Habib has been involved in the development of large-scale cosmological simulations, the MC2 and HACC codes, and related analysis tools. He has collaborated to solve scientific inference problems in cosmology using a finite set of supercomputer simulations. His current interests cover issues in data-intensive computing, including applying ideas from statistics and machine learning to elucidating physics problems.
Please join me in congratulating Dr. Salman Habib at the 2020 IEEE Computer Society Sidney Fernbach Award recipient, and we look forward to your presentation.
Well, hi everyone. It's a little funny to give a talk without seeing an audience in front of me, and I'm sure it's the same for you. But I would like to begin my talk by thanking very much the IEEE Computer Society for the Fernbach Award, which I have to say came as a complete surprise, a very delightful surprise. And I should also explain from my point of view, because I'm really a theoretical physicist, and I'm not in a very real sense a deep computational scientist. But I love using supercomputers as tools for gaining insight and to solve hard problems. And from that perspective, I found that working with them has been a real pleasure. Of course, it has had its ups and downs over time, but it's been also great working with a very, very interesting community of people. And on this slide that I'm showing, the very first slide, are just images from a whole bunch of different applications, all having to do with things like cosmology and quantum mechanics and accelerator beam dynamics and precision calculations in field theories, and all of which have been made possible by supercomputers. And aside from working with these machines, what's been interesting also is to work on the infrastructure that's required to solve these problems or help other people fix the infrastructure, such as networking. And one image on the far right is the thinking machine CM5, which was, still remains my all-time favorite supercomputer, and I'll explain to you why. So as a personal history of supercomputing for me was my first encounter with a supercomputer happened at Los Alamos when I was a postdoc there in the early 1990s. And what happened was that I had listened to someone give a talk on a stochastic field theory problem, and I said, surely that can't be right. We should be able to do better than that. And I was talking to Frank Alexander, who was then a postdoc there, and he kind of introduced me to this idea of running simulations on SIMD systems. At the time, we had a CM200 that was given to Argonne by Thinking Machines, given to Los Alamos by Thinking Machines as a test bed for people to try out various things. And what was quite remarkable about that system was that, aside from being a powerful machine for its time, it was so amazingly easy to use. And within literally a week, I was up on CMF and C star, which were the SIMD languages the machine supported. And I had to record a great debt to Leonard Johnson and his group for CMSSL, which later on I used quite a bit on the Connection Machine 5, which was our next system, and which was at that time the world's most powerful machine. And I also have to acknowledge a large number of people I worked with at at Los Alamos. I'm only showing you pictures of a few. And it was a real pleasure working with all of these people and continues to be. And the other interesting thing there was that aside from the initial group of people at Los Alamos, there was also very interesting connectivity with all the other national labs and the computers that they have, which has continued to this day. So moving on, so the question is, what was the situation like in the early 1990s, and how is it different today? And at the time, it was kind of interesting because we were making the transition from vector supercomputers to parallel machines. And at some time, I mean, now it seems pretty obvious that such a thing had to happen, but it was not very obvious at that time. And there were people who were arguing that these parallel systems would be useless, would not work. I mean, yeah, it's hard to imagine now, but it's true. Fortunately, it's good to be inexperienced and not know any better. So I could try various things, and they all seem to work just fine. So that was pretty straightforward and easy. But things have changed, and this supercomputing landscape now is very different from what it used to be in the 1990s. So let's take a look at the many faces of supercomputing and ask the question, well, why is supercomputing so important? Well, obviously the answer is multifaceted, and one classical place for supercomputing is to solve canonically hard problems like computational fluid dynamics, lattice QCD, n-body interactions. These are problems that are hard computationally, and as machines improve, we can do a better job. The other interesting thing that's happened with supercomputers is that not only have they gotten, in some sense, faster, although in a weird way that's sort of debatable, but they have gotten a lot bigger, and that's not debatable. And therefore, we can actually do a lot more interesting things when trying to understand or make predictions for very complex systems, such as systems are relevant to material science, biology, biomedicine, chemistry, complex chemical reactions, astrophysics, and obviously geophysical modeling. So that's been a big change. And the other interesting thing is that once you can do such complex simulations, you can also do many component system scale simulations. So it's not even enough to say, well, it's multi-physics and multi-scale. It's actually system scale. So lots of things can be glued together. So you can imagine simulating entire cities, the climate, the entire universe, reactors, other complicated things like wildfire. So these are things that supercomputers can do, which they could not before. Then there are other very interesting applications like large-scale inverse problems, including optimization. And what is even more interesting these days is the fact that previously supercomputers, you gave them a simple question. You said, well, solve this equation and give me the answer. And the answer might just be a single curve. And now you actually feed them a lot of data, and the answer might be a lot of data back. So one big use of supercomputers in the future is going to be obviously AI and ML applications. And so I would say that supercomputers today are very different from what they were when I started, much more interesting and much more difficult to deal with. So for this reason, I think it's really important for people who are designing applications for these machines to keep in mind the timescales of interest and the complexity of the problem, right? The problems have to be intrinsically difficult, obviously, otherwise you wouldn't go to a supercomputer. And there has to be a continuous addition of complexity. You shouldn't say, okay, if I solve it now, I'm done, because there's just too much effort required to do that. You should think it's a multi-year kind of problem, and it should be much longer than individual supercomputer lifetimes. So one of the tragedies of a supercomputer is that its life is short. Supercomputers are definitely live fast, die young, right? So again, this is a community to which I'm speaking that completely understands this. But the first year you warm up on a supercomputer, things aren't working very well, software isn't ready, there's some unknown hardware difficulties. The first year is kind of like a warm-up typically. Sometimes things go very well, but not always. Then you have 3 years of useful work, and then there's an end period of slow obsolescence. So a machine that was started to be a fantastic object in 5 years is done, right? So one of the tragedies of life working with supercomputers is because to me they become almost personal friends, funny way of talking. And I've had many such personal friends over the years, starting with the connection machines. And it's been kind of sad to see, they come, they go, and unfortunately people don't do a very good job of maintaining the history of these systems. So sometimes if you look back and say, oh, I wonder about what was done on this machine, or what some features of it were, and so on, is really, really hard to find. So that's kind of the tragedy of supercomputing, that you work so intensely on these systems and then they kind of disappear. So coming back to the supercomputing experience today and contrasting it with what it was when I started, there is actually a big difference, because in those days we were basically looking at, or at least I was looking at, as a supercomputer as basically a much, 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 much faster version of a workstation. I could program on it pretty easily. One person could write a new code literally in a few days and do something completely different. And there weren't that many users on the machines as well, so you felt like you were engaging with a system on a daily basis. But of course, if you contrast the situation then with what it is now, it's completely different. And I would argue that supercomputing is not for everyone, because high-performance computing programming is pretty tedious, as we all know. The system interactivity is actually also pretty poor because of batch processing and long queues. You submit something, you hope for the best. The file systems continue to remain, even though they're very large, they continue to remain a source of instability. And the high-performance computing software suite is, I would say, somewhat less than elegant. And it is certainly not as nice as what you can run on your laptop. Then there's the usual system crashes and downtimes. So you have to be a person who can take some abuse, I think. That's pretty clear. However, it's worth it, right? Because what supercomputers can do, nothing else can, right? I mean, that's a really, really important point. So despite this high bar for entry, meaning a certain level of talent, a certain level of being able to take abuse, the supercomputers are really, really fun, actually. And supercomputing, in my mind, isn't hit and run. You don't say, I solve this problem, I go away. The science impact is really, really important and has to be commensurate with the effort you put in to actually get something running on the machine. And for this reason, a big picture view is really necessary, especially now with the machines being capable of doing so much. And it not only just covers the computational aspect of running on these machines, but also, as I said before, data comes in, data goes out, data management is a big issue. Moreover, analysis is a big issue now. It's not just enough to run something. You have to do in situ analysis as the code is running. You have to have offline analysis modes that are as performant as your code. It's basically, it's a whole ecosystem that you have to control. And for that reason, you have to think in terms of long-term, basically long-term thinking. What are the roles of scalability, of performance? How is my code going to evolve? And remember that supercomputers don't live long, so the hardware is also going to change. And that is actually much more significant than now, because in the 90s, there was this idea of a balanced system, and people were thinking, you would make machines with gap factors of order 1, and that would be fine. But now machines are extremely hot in the sense that the nodes, especially accelerated nodes, are extremely fast, and you don't have a very large number of these nodes. But nonetheless, the connectivity between these nodes and even their internal connectivity is not that great compared to the performance at the node level. So, and this could be changing in the future. So because we don't know what the hardware changes are on a time scale of, let's say, 5 years, it's extremely important to watch out when you're writing the code. And this is particularly important for small teams. Anyway, I just want to end by saying that it's clearly not a one-person do-it-all situation. And the team context is very important. So I think one of the key things for me working with supercomputers is also the fun one has working within a team. And I think this is really one of the crucial aspects, nice aspects of supercomputing. So having said all this earlier stuff about what really constitutes a good supercomputing project, I want to talk a little bit about the story of HACC. And HACC is the Hardware Hybrid Accelerated Cosmology Code. And I think it's a kind of interesting story, and I won't go into many technical details. I mean, this talk is not about technical details. And it's mostly about, big picture views. So why is cosmology a good supercomputing exemplar? That is an interesting question. And obviously, if I say, well, look, I want to model the entire universe, you're not going to believe me if I say that's a very simple problem. But the point is, obviously, one is not trying to model the entire thing, but only a set of observations that can tell me a lot about the science of interest. As it turns out, the problem is obviously complex, but it is sufficiently well defined. And this is actually kind of remarkable, and the reasons of this are complex and in some sense straightforward, maybe not complex. But one interesting point is that the initial conditions for the universe are very simple. Why they are so simple, by the way, is somewhat mysterious, but they are. And so starting a simulation is actually relatively straightforward. It's also surprising that the number of parameters, as far as cosmologists are concerned, fundamental physics parameters, is small. It's of order 10. The number of modeling parameters, of course, is much larger and can be in the hundreds, but the science itself can be defined by a relatively small number of parameters. So that's kind of nice, because it's not, even though it's system scale, it's not hugely complicated. The other interesting thing to keep in mind, obviously, is that the science itself is absolutely fascinating, right? Cosmology is where we've learned about things like dark energy. Why is the universe accelerating? We don't know. What is the nature of the dark matter that surrounds us? We don't know. We would love to find out. We know it's there. We can do lots of interesting things now with gravitational waves. We can test Einstein gravity at amazingly large scales. We can learn about the early universe because of the speed of light. By looking at farther distances out, we're actually looking backwards in time. So cosmology is absolutely fascinating from that perspective. Aside from these theoretical interests, what is also amazing is the sort of growth of instrumentation, which has been absolutely fantastic. And there is a large number of new surveys, and I've shown some of the images here, both space and ground-based, covering a large number of, covering a wide range of frequencies, because everything is basically photons that we get from the sky, but in different wavebands. And the data that we get, and I'll explain a little bit more about that, is absolutely beautiful. And in fact, there are many things that we can measure with accuracies at the percent level, which is quite remarkable. But it means that as a theorist, you have to be able to make precision predictions at that level. And this is simply impossible without supercomputing. So this is a great place for many talented people to come together, work on a variety of science problems involving the theory and modeling of the equations, new algorithms to run them on the machines, work on next generation hardware that, both on the instrumentation side and on the compute side. The problems are both compute and data intensive. There's a very good place to apply AI, ML, and advanced statistical methods. So it's actually a very, very nice place for everything to happen. So just to give you an idea about where things are with cosmological observations and why supercomputers are so important, I show here, if you look at the top left, there's a compilation of results from 1999. So that's not so long ago, right? About 2 decades ago. And this is from the cosmic microwave background, and it tells you about the temperature fluctuations on the sky in the microwave sky. And as you can see, the observations are all over the place. So the temperature fluctuations are shown here as a function of the angular multiple. So large scales are to the left and small angular scales are to the right. And you can kind of see that the data is consistent with some sort of bump, and the bump is predicted by cosmological theory. But it's hard to say how well you really got things. And then fast forward to 2013, which is only 14 years from 1999, and the results are absolutely stunning, right? So the results come from the Planck satellite, and the theory lines go bang through the points, right? So it's just amazing stuff. Now, at the bottom left, you can see a similar thing, but instead of looking at the microwave sky, we are now looking at the distribution of galaxies in the sky, and we're looking at a 2-point correlation function, which is basically telling us how galaxies cluster. So it turns out galaxies don't live on the sky randomly. If you find a galaxy, then chances are you'll find another galaxy closer to it. So this is exactly how they're distributed. One very simple thing is to measure the 2-point correlation function. So there's a bump in the 2-point correlation function, the baryon acoustic oscillation bump, that roughly speaking corresponds to the same physics that you saw in the CMB, right? And that bump can only be seen if you can do a survey large enough. And the scale of the bump is 100 megaparsec. A parsec is 3.26 light years, so a million times that. So it does mean that you have to have a survey that's significantly larger in order to see this feature. And again, this feature was seen by the Sloan Digital Sky Survey first, and then later on with deeper surveys. And as you can see, this is a result again from 2012. 1999, we just didn't have surveys big enough or deep enough to see it, but in 2012, we saw the bump exactly where it was predicted. So what we have seen now that in cosmology, we have a massive increase in sensitivity, and we have massive increase in volume and depth of the surveys. So all of this requires obviously precision prediction, and you have to run these big simulations, right? So what are these simulation requirements that have happened, as a result of what I just told you? And so starting in the 1990s, we could do cosmological simulations that were applicable to like a single probe of cosmology, like say galaxy surveys. And that was possible with terascale computing. And then in the 2010s leading up to now, we've been able to do simulations for what I call second generation surveys, where we can simulate at the same time multiple probes, not just one at a time. And the accuracy is, I would say, intermediate in the sense that our understanding of the observations and our understanding of the theory needs to be improved significantly. And we hope to do that at the exascale in the 2020s. And that's basically what a large chunk of the community is working towards. And this has been an amazing change, because the first cosmological simulation, I shouldn't say it's the first, but one of the first was done actually in 67 years a mistake, probably 68, 69, by Jim Peebles. I'll talk about a little bit on the next slide. So, and that will give you an idea of how far we have come and what supercomputers have allowed us to do. So one of the very early cosmological simulations was carried out by Jim Peebles, who, by the way, won the Nobel Prize for cosmology last year. And this was to look at the structure of the Coma cluster. And this was an n-body simulation that was done with only 300 particles. And this was done when I don't remember exactly, but I think Jim told me that he was spending a summer in Los Alamos, and they gave him time on a CDC 3600, which was by no means a cutting-edge computer at the time. And that's where he did the simulation. And but now we are looking at, we are 10 orders of magnitude faster now with computing, so hopefully we ought to be able to do better. At the same time that Jim was doing his 300 particle simulation in 1969, Bob Dickey gave a series of lectures where he said, this is all hopeless. The universe is far too complicated a structure to be studied deductively, starting from initial conditions and solving the equations of motion. Well, he was wrong, okay? We can do that. So what is, the current scenario in cosmology? So what it is that we are basically treating cosmology as an inverse problem. So clearly, we can't do lots of things that we can do in normal science. In a normal scientific scenario, you can, if you are confused about something, you can always run an experiment. And you can, in many cases you can, and sometimes you cannot. But when you can, you run an experiment. And if you're confused about something, you say, okay, I'm going to try and make sure that other things that can confuse the result are not part of this experiment. I can sufficiently isolate things from each other, and I can focus on the things that the parameters that are of interest. That is essentially one of the basic things underlying a scientific method. The problem with things like the climate and with the universe is that we cannot really run experiments. So no matter how good our budget is, it's very hard to construct another universe. So, but what we can do is we can simulate other universes. So what we can say is, all right, if we can build a universe simulator which is sufficiently realistic, then we can run pseudo experiments on our simulator, and then we can say, well, given that we have one universe and we repeat the same exercise on that one universe, how well can we learn about that one? So that fundamentally is one way of thinking about it. So how does cosmology work scientifically? Well, on the extreme right of this picture, you see multi-wavelength observations that I talked about. So telescopes of various kinds. So we get a set of observations. Now, from these observations, we get a set of statistics. So the observational campaigns provide statistics. So cosmological probes are all statistical in nature. So you measure multiple correlation functions and so on. And now that is your data. And you have to match your data to all possible predictions that will come from simulations. Now the difficulty with this is that, as you can imagine, running a universe isn't an easy job. So even if you could run one simulation that had all the physics of interest, it might take you weeks or months on the state-of-the-art supercomputer of the day. But one of them isn't going to be enough because, as I said, there are tens of physical parameters and hundreds of modeling parameters. And you can only run a simulation with one choice of those. But if you make the wrong choice, sorry, results won't agree. So clearly, when you're forward modeling this thing and using a Markov chain Monte Carlo framework, in your simulation campaign, you have to start thinking about how many simulations do I need to run. So if you do some naive calculations, you discover very quickly that you need to run perhaps 1 million simulations. Well, that's not going to happen. So you have to come up with various sampling methodologies that allow you to run a much smaller number of simulations and still be able to make predictions that are of sufficient accuracy. So that is something that we are actually working on quite hard. I don't have the time to talk more about that, but there is a technology called emulation, which we push very hard, and essentially now I think pretty much everyone agrees that this is the right way to do things. So what we do is we do a smaller set of simulations, but we have a way of extending it to a large number. But the way the simulations are done is they're fully realistic. So let me go to the next slide to explain this. So you start, as I mentioned earlier, with some relatively simple initial conditions. You run a cosmological simulation code, which may have gravity and hydrodynamics. It gives you cosmological structure, which we'll come to in a second. And then you have to do a large number of analysis tasks, and you have to follow the photons from these fake galaxies all the way through the atmosphere, to the telescope that you're modeling, to the data system, everything. And because you need to be, as I said earlier, you need to do this full end-to-end analysis. So there are two panels in the center of the figure that I'm showing. So the one on the left actually is a simulated image, and the one just to its right is a real image from the Magellan telescope. As you can see, the realism is pretty spectacular. On the right side, there's a picture of an end-to-end simulation for the galaxy distribution as will be seen by LSST, and this is based on a full system scale simulation. So we are in a situation now that we can make synthetic skies look so much like the observation that you can fool some observers. Not for very long, but at a first look they'll say, wow, that's pretty impressive. So what does it take to simulate the universe? So now we are at the place where we can talk about the actual calculations. So the key role in structure formation is clearly that of gravity. And what happens is the universe is expanding. So there's an instability, which is a gravitational Jeans instability. And it's because the universe is expanding, this instability, which otherwise would be exponential, is weakened. And it basically becomes power law in time. So even though you have some very smooth initial perturbations, they will grow and form all the structure we see today. And this growth is described by a 6-dimensional Vlasov-Poisson equation, which for people from the plasma physics community looks very, very familiar. And it's basically a bunch of particles interacting by Coulomb forces. Yes, the universe is expanding, but that's just a minor detail. And it's the wrong sign because gravity is attractive rather than being repulsive. And the fact that gravity is attractive but has only one sign, there's only one kind of charge, there's only mass, there's no shielding. So short range, all the long range forces are not shielded. And therefore, when you try to solve a Vlasov-Poisson equation, you need a very, very large dynamic range. And the dynamic range that we need, and I'll explain that in a second more as we go further, is about 1,000,000 to 1 spatially, which means that the smallest scales of interest, the ratio of the largest scales of interest to the smallest scale of interest is roughly 1,000,000 everywhere, right? So this is a very, very difficult simulation. And then at the same time, we also need to add hydrodynamics to the simulation and various astrophysical subgrid models to make sure that we know how to put stars in, we make sure what normal hot gas is doing, etc. And I won't have time to talk about that here, but that's very important. And once you have all the matter taken care of, the dark matter and the normal matter, then you also have to do some phenomenology. We also have to put, galaxies and other things there. We have to calibrate simulations against observations. So that's what the code HACC was basically designed to do, basically have a scenario where we can do a large number of these simulations relatively quickly, because we also want to solve this inverse problem. So the prehistory, and so aside from the people at Los Alamos who you saw earlier, our group moved to Argonne in 2011, and so here are people who are now part of the HACC core team, and there are other people as well. I couldn't all fit them here, but credit goes to them for working on the code. So the prehistory was that we wrote a code called MC2, mesh-based cosmology code, which was a parallel PM code written by modifying a beam physics Poisson solver that had originally been written by Rob Reiner and myself and Ji Chang, who came later on. And then, this is one of the nice things about working in multiple fields, where you say, oh, I can do this, and I can simply take what I had done earlier, flip a sign, and guess what? Well, it's not as simple as flipping a sign, but close enough, and you get a cosmology code. Well, what's interesting about this is that in the late 2000s, Los Alamos decided to build the world's first petaflop system, which was Roadrunner, which was the first accelerated system, CPU and IBM cell. And that time we said, oh, we should really do something new. We were asked to do something new for Roadrunner, and that's where the original design of HACC comes from. And the interesting thing is that we were forced to think about designing a code for a machine that would go behind the fence very, very quickly. So there's no point writing a code that would run on a machine that's only available for 6 months, right? So we had to write a code that we would be certain would last for a much, much longer time. So that was a design imperative, and then later on that code became HACC, was implemented on the BGQ, on Titan, so now it runs on every supercomputer. It also has a new hydro algorithm, which work on which was led by Nick Frontieri, and I don't have time to describe that. But I'll tell you a bit more about HACC and how well it works. So basically, as I mentioned earlier, HACC is about doing very high resolution cosmological simulations. The design imperative is pretty much clear. The other thing is it needs to be developed and supported by a small team. It's not a community project. It has been very successful. It was the first, in some sense, true production science code, meaning lots of science papers have been written with it to break 10 petaflops sustained. And the other thing is it combines a large number of, not a large number, but multiple algorithms using a mix and match approach, so which allows us to vary the code as the computer hardware underneath changes. It has very good strong scaling properties, but what we need, because cosmology, we're looking at very large scale problems, must have perfect weak scaling, and it does. So one of the problems with dealing with building a new code is you always have to ask yourself, what's going to be available and what is my problem? So people always keep telling us, don't worry, there'll be a fundamentally new language and there'll be a great compiler, and you don't just wait, everything will work. Or there'll be a special purpose machine built just for you, but cosmologists are poor, that'll never happen for us. So, but the top part, these HPC myths in some sense, have just not played out for the most part. So one has to follow the HPC reality, which is know what the architecture is, know what the boundary conditions are, what kind of machine you're going to get, and realize that you may have to do a lot of fiddling and a lot of rewriting, a lot of rethinking. There's not going to be an easy code port. So it's very important to think out of the box. It's extremely important to get a bunch of smart people together and work together to make things happen. So the underlying principle behind HACC is basically, so I think basically you have to think at a higher level now when you're thinking about the fact that you deal with different architectures. It is enough to simply say, well, first I go from physics to the math, and then math to the computer is kind of like a unique solution. That is not true. Math to the computer has a lot of openness to it. You can say, I can solve a partial differential equation by using a grid. I can solve a partial differential equation by using a stochastic method. I can solve a partial differential equation by using particle methods. So the method space is something that should be really viewed as an open thing, and that is really very important. So the fundamental physics idea behind a cosmology code that we used is that there's a smooth long-range component and there's a rapidly varying short-range component. So that allows us to immediately break the force calculation into two parts. And the long-range part is done on a grid using a high-order spectral method, which was specially designed. And that's one of the unique facts, unique elements underlying HACC, which is that it has a high-order quiet spectral method. And the small scales are then handled by direct solvers, which depend entirely on the architecture. So the dynamic range of around 10,000 is handled by the smooth part of the code, and the sort of crucial short-range dynamic range, which is of a factor of around 100 of dynamic range, is handled by the short-range solver. The other thing that the code has is also what I call scale isolation, meaning the short-range part almost does not interact with the long-range part, and that makes life extremely helpful when you're tuning the code. So that was sort of like the physics angle on how the code is designed. And the architecture angle is that you have to optimize for next generation code ecology. So you have to be, keep track of the numerical methods you're using, the algorithms. We use mixed precision, for example, and that helps working with GPUs. We also have a good sense of data locality. You have to worry about all of these things, as I had mentioned earlier. The code design of HACC is basically a kind of universal top layer that works on all machines. And then there are optimized node level components that you simply plug in and out depending on what the architecture is. Roughly 95% of the lines of code live in this universal top layer, and about 5% of them belong to these highly performant kernels, which are of order 10-ish kernels or so, which change as you change the architecture. So this is actually very nice because it means that we can focus entirely on these things when it comes to a new piece of hardware that we have to deal with. We also have to stress, because we run on the full machines, we also have to stress scalability, low memory overhead, and platform flexibility. Basically, we don't have a machine that someone gives to us and says, run your code on this machine, it's all yours. We have to basically scrounge for time wherever we can get it, so we have to make sure we can run on all possible machines. So optimal splitting of the gravitational forces I already mentioned. So we have the spectral particle mesh methods along with tree force solvers. And there's things we do to manage the compute to communication balance. I don't have time to say too much more about that right now, but the important thing is that it all works. So in pictures, how this happens is that there's an overall 3D domain decomposition. The nice thing about cosmology is that the boundaries conditions are quite straightforward. They're periodic. And so you run simulations typically in 3D cubes. And so there is a first level of HACC is basically 3D domain decomposition, where we use particle replication at boundaries, which is kind of another way of implementing a ghost zone that isolates the regions from each other. And then within each of these things, there is a HACC nodal layer, which are the short-range solvers, which handle the short-range forces. So there's a chaining mesh that connects from one to the other. And then within these, there are trees, which we call bushes, because each of these meshes is connected to a single tree. And then within these trees are the levels for the short-range solver. So it's kind of a complex beast, but the fact that you can break up these tasks in this way really helps. So now to actually show you a movie to show that everything actually works, here's a movie of a simulation. So everything starts from the beginning with a very smooth initial condition. And this is a simulation which has more than 500 billion particles were run on Titan a while ago. And what you're seeing is a 1/16,000th of the actual simulation. So the simulation gets started. And you can see structure is forming, and structure formed initially something like smoke settling almost, right? The initial smooth distribution breaks up, and the gene's instability is taking over. And initially what happens is the first part of structure formation is kind of quasi-planar collapse. Then where the planes cross, you see filaments forming. And then as the filaments intersect, you see nodes, you see which are basically the halos, and the halos are clumps of matter, and inside those halos are where the galaxies will be forming. And the halos form within the filaments. So it's really quite a beautiful structure, and it's called the cosmic web. And this is not noise. If you run the simulation in exactly the same way, you get exactly the same result. So, and what you're seeing right now here is as I said, it's a very, very small piece. So just to give you an idea, this is a chunk, a 29 by 29 by 58 megaparsec divided by h. H is a factor, don't worry about it, of order 1, of a 923 megaparsec over h box. So it's a tiny piece of a simulation. So you can just imagine, if you took the big box, what the dynamic range of such a simulation is. So that was basically my talk. I just wanted to give you a feel for, how a cosmological simulation runs, what went into its design, and I wanted to keep it fairly high level, and how all of this is a lot of fun actually, and it's connected to really beautiful science. So now I just want to summarize with some few lessons that we have learned, and I start with a warning because obviously not everything below applies to all supercomputing codes. That is definitely not the case. However, the lessons that we've learned are that thoughtful design of flexible code infrastructure is really important. Minimizing the number of computational hotspots and isolating them is key. And the fact that we can use multiple algorithms is a big plus. And exploiting domain science expertise is really, really important. So I think it's a mistake when often people work, on the domain science side with computer scientists or computational oriented people. They say, well, this is my problem, and they give you a very well-defined thing, and they say, go solve it. That actually may not be their problem. Their problem may be something else. So it's always good to get a higher level view of what the problem actually is. And this requires learning each other's language, and this often takes a year or two of talking to work this out. One of the big issues that we have to deal with now is that machines are very out of balance, as I had mentioned earlier. And so it's also a mistake to focus only on the lowest level compute intensive kernels, because maybe the task was somewhere else, right? Maybe you should have just thought harder about actually how the code is structured, rather than worrying about getting a factor of 1.5 or 2 or even 5 out of the lowest level compute intensive kernels. So what we found is this method of an overarching layer, a 2-layer code. Now that may or may not work for everyone, but that's something that we found worked for us. It's extremely important, and everyone knows this, so I'm just flogging a dead horse here, is basically the fact that you have to minimize data motion. And understanding the data motion in your code is really important. And that is a truism, but remains really, really true. And I think the other thing is that one needs to be able to change one's code on fast timescales. So one thing that we've discovered, and by the way, it's no mystery, is that you have to work really closely with people who understand performance on the hardware. So in other words, the performance engineers. And if you want to work with them, you have to work at their level. So you cannot work with opaque libraries, because A, they may not be ready, B, and in fact they might not, is a nice way of saying they will not be ready. And if something goes wrong with them, we cannot fix them. So one way to be able to change things on fast timescales and work with people who actually understand the machines is to have everything under your control. Now, this I know is not practical for everyone, but this is something that has worked for us. The final thing I want to point out is that as science outputs are becoming more and more complex, the data analysis is becoming, and has been for some time, and actually in many fields, a really significant fraction of the available computational time. So people have to start thinking in a way that's distinct from what happened earlier, which is we thought essentially about solvers and not so much about analysis. And I think now we have to think more and more and more about analysis, which is a topic for a completely different talk. Anyway, thanks very much for your attention, and I'm ready for questions.